Professor Rad, and this is Precalc video 111, the Extreme Value Theorem. So radical. So in this video, we're going to talk about the Extreme Value Theorem. And in this course in particular, we're not going to do a lot of formal proofs. So we have something, I have a visual argument to make here. This isn't quite a proof, but it kind of gives you the idea behind it. Yeah, so why don't we talk about the theorem, and then we'll talk about visually why it seems like it ought to be true. So the Extreme Value Theorem says that if f of x is a continuous function on a closed interval, that means you're including the endpoints, then f has an absolute maximum and an absolute minimum on that interval. So let's see why this might be true. So I'm going to start out by creating a coordinate plane. And I'm just going to look in the first quadrant just to make life easy, but you could do this however you wish. And I'm going to pick a value for A and a value for B, since we're defined on this closed interval from A to B. Now, because our function is defined on this closed interval, that means when x is A, there's some y value, and when x is B, there's some y value. So for instance, maybe this is where f of A is, and maybe this is where f of b is, somewhere up here. So my task, in order to say disprove this theorem, try to come up with a counterexample, would be let's find a way to connect these 2 points in a continuous manner so that, let's say there's no maximum value. So if I just connect these with a straight line, I've already failed. Because remember that absolute max and absolute min can be endpoints of your function. So in this case, the absolute maximum is happening here at the end. So if I want to try and avoid an absolute maximum, that means that at some point I have to be higher than that. So maybe I'm like something like that, right? So now this is no longer an absolute max. But now we have a problem, because now we have an absolute max there. So there's some value here that has a maximum y value. So what if I put a hole there? Now we have to be defined on this closed interval, so maybe it just like skips right here. So now here's a question. Does this function have an absolute max? It doesn't, because it would be where this hole is, but we fixed it, so now it doesn't. However, it doesn't apply to, the theorem doesn't apply to the situation. Why not? So by doing that, by creating a hole here, we've now made a function that is not continuous. So this function has a discontinuity at this point. So this theorem doesn't apply. The theorem only applies to continuous functions on a closed interval. And this is not a continuous function. So you can try and do some other things, like maybe pick a point for A that's taller than the point that you have for B, but you're going to run into the same kinds of issues. This time the maximum is happening at A instead of happening at B. So that would be your challenge. If you were to try and disprove this theorem, you want to find a function that has a point at A and it has a point at B. Oh, maybe if I have a horizontal line. But that's not going to work either, because in the previous video, we saw that when you have a constant function, it's both a max and a min. So here our absolute max is our absolute min, whatever that y value happens to be. Maybe you're thinking, okay, what if we had something like this? And maybe we're defined here. Right? So we're defined on this closed interval. So we include both points, but we have this vertical asymptote. But this function is, again, not continuous, because in order to draw this point, I have to lift my pen from here. And if I don't have a point defined there, then I'm not defined on a closed interval, because I'm not defined for B. So you can try and do that. You can try and find a way to connect a point at A and connect a point at B so that there's no absolute maximum but you're going to fail if that function is continuous. And the only way to succeed is if the function's not continuous, so the theorem wouldn't apply. So like I said, this isn't quite a proof. This is sort of a visual attempt to disprove the theorem. And because we failed to disprove it, we're going to say it's true. Again, that's not a formal proof, but just to kind of give you an idea, when you mess with these things, that kind of gives you an idea, helps form your intuition about why such things might be true. So I hope this was totally tubular. It was a very extreme value theorem. Hope that helped kind of define what this is a little bit. It just basically says, if you're on a closed interval, you can maximize your profits or you can minimize your costs, right? There is a maximum, there is a minimum. You'll be able to find it on a closed interval. So hope this helped with the extreme value theorem. And I'm looking forward to seeing you in the next video. So bye for now.